In this video, I'll conclude my lecture on cosmology. I'll talk about what the universe is mostly made of and what lies in store for the future. Most of the matter in the universe appears to be in a form that we haven't detected directly. We call it dark matter. It doesn't emit, absorb, or reflect any light. And by light, I mean the entire electromagnetic spectrum from radio waves to gamma rays. But we need this dark matter to explain many things that we do see. Without dark matter, galaxies couldn't have formed and couldn't stay together. Here's the rotation curve of the Milky Way galaxy. If the visible matter is all of the matter, then it should be orbiting slower in the outer regions of the galaxy, as shown by the blue curve. In reality, the outer parts are moving just as fast as the inner parts, as shown by the red curve. That means a lot of dark matter is required to hold the galaxy together. We see the same thing when we look at other spiral galaxies. So all spiral galaxies appear to contain mostly dark matter. Stars in elliptical galaxies orbit in random directions, but they're also moving way too fast to be held together by just the visible matter. So all galaxies are mostly made of dark matter. In galaxy clusters, the galaxies themselves are moving too fast, and so there's plenty of dark matter between the galaxies, on top of all the dark matter inside of the galaxies. So what might this dark matter be made of? Astronomers have come up with two super cute acronyms. Some of the dark matter could be in the form of faint objects that are made of ordinary matter. These could be things like black holes, neutron stars, brown dwarfs, and planets. And we'd need a lot of this to lie in the halos of galaxies to explain galaxy rotation curves. So these hypothetical objects are referred to as massive compact halo objects, or MACHOs. Another possibility is that some or all of the dark matter is not made of ordinary matter at all. In other words, unlike stars, planets, moons, gas, dust, and everything else we can see in the universe, it's not made of protons, neutrons, and electrons. It's made of particles that we haven't yet detected directly. These are called weakly interacting massive particles, or WIMPs. In the 1990s, when the first big neutrino detectors were being built, astrophysicists thought dark matter could be made of neutrinos. These detectors have since shown us that there isn't nearly enough mass in neutrinos to make up much of the dark matter. So neutrinos don't fit the bill, and neither does any other known particle. But despite this, most astrophysicists do believe that most of the dark matter is made of WIMPs, not MACHOs. This might sound ridiculous to you. Let me explain why we believe this. One reason is that we don't expect there to be many MACHOs out there. Take black holes and neutron stars, for instance. They're produced in type 2 supernovae. Only the most massive stars become type 2 supernovae, and these types of stars are rare. At the other end of the mass spectrum, we have the small things like brown dwarfs, planets, moons, etc. We do expect there to be a lot of these out there, but their combined mass is expected to be way too small to account for much of the dark matter. Remember that all of the planets, moons, asteroids, and comets of the solar system put together still account for less than 0.1% of the mass of the solar system. The sun accounts for over 99.9%. So there just isn't enough ordinary matter. On the other hand, there could be all kinds of particles out there that we haven't yet detected. We shouldn't be arrogant and assume we've already detected everything that's out there. Neutrinos were only discovered in 1932. I'm sorry, neutrons were only discovered in 1932. Neutrinos weren't discovered until 1956. Here are some other particles that were discovered since then. W and Z bosons in 1983, the top quark in 1995, and the Higgs boson in 2012. You don't need to know anything about any of those particles or remember any of those dates, but the point is that there's no reason to think we're done discovering fundamental particles. Any particle that doesn't interact with protons, neutrons, electrons, or light is hard to detect. Several such particles could have been made in the Big Bang. In fact, we need these types of particles to explain how galaxies formed. The only cosmological simulations that are able to reproduce the observed distribution of galaxies are the ones that include lots of WIMPs. There wasn't enough visible matter to collapse proto-galactic clouds to form the first galaxies. Most of the gravitational pull had to come from dark matter. Previously, I described the events that took place during the first 375,000 years of the universe. Then, during the first billion years, tiny clouds dominated by dark matter collapsed to form the first galaxies. These merged together to make larger galaxies, and those larger galaxies merged together to make even larger galaxies. Eventually, two large spirals emerged in the local group, and inside it, a star was born 4.6 billion years ago. At least one of its planets was at the right distance to have liquid water on its surface once it settled down after the violent formation period. Soon afterwards, life appeared on this planet. All life forms on this planet have a few things in common. They're all made of cells immersed in water, which reproduce following instructions provided by DNA, which is a chain of certain organic molecules. Over the last century or so, biologists have discovered that we're nearly identical genetically to chimpanzees. We have more distant relatives in the ape family, such as gorillas and orangutans. Apes come under mammals. So do dogs, cats, elephants, rats, horses, pigs, and whales. None of these appear on the tree of life shown here. That's because all animals, including mammals, but also birds, reptiles, insects, etc., make up one twig on the tree of life. All plants, from a miniature potted plant on your windowsill to a giant redwood, make up another twig on the tree of life. Mushrooms and other fungi make up another twig. Slime molds get their own twig. The overwhelming majority of life forms are single-celled organisms, such as bacteria. For the first 3 billion years, only single-celled life existed on the Earth. Then there was an explosion of complexity. Eventually, there were animals with backbones and trees. And then dinosaurs, and finally, mammals. Dinosaurs dominated the land until 66 million years ago when an asteroid impact wiped them out. Since then, mammals have dominated. In just the last 100,000 years, one mammal, humans, started to become dominant. This intensified around 10,000 years ago, and over the last 100 years, we've completely transformed the planet. That's where we fit into the big picture. It's hard to predict what lies in store for us, humans, over the next 100,000 or even a million years, but we do know what's going to happen to the Earth in a few billion years. The sun will turn into a red giant, ballooning up so much that the Earth will be inside of it for a while. Meanwhile, the Milky Way will be colliding with the Andromeda Galaxy, which will lead to all kinds of chaos. How about the universe as a whole? Is it going to keep on expanding, or will the expansion eventually stop? The key question is there enough gravity to stop the expansion? If there's a lot of gravity, the universe could soon reach a maximum size and then start contracting until we have a big crunch. If there's slightly less gravity, it will continue expanding, but slower and slower over time. Those are the two scenarios shown on the left. If gravity is negligible, the universe will expand at a constant rate. It'll just keep coasting. The only other possibility is that the universe will actually speed up, not slow down, in its expansion. Well, guess what? That last scenario, which might have seemed least likely, is what we actually see happening. Galaxies are moving away from us, not at a constant rate or slower over time, but faster over time. Something is accelerating the expansion. There appears to be some energy in the universe that is pushing it apart faster over time. We call it dark energy. What is dark energy? We have no idea. Just like dark matter, we've never seen it directly, but it's making things move faster than they would otherwise. Something is making the universe expand faster over time, and since we can't see it, we call it dark energy. So how will the universe end? If things continue as they are now, the universe will keep on expanding. Eventually, all the stars and all the galaxies will die, and no new ones will form. As the galaxies fade away, they'll also move further and further apart, eventually disappearing from view. The universe will just get colder and emptier. If you find that depressing, let me remind you that this is tens of billions of years into the future. If you want something to grasp onto for hope, I'll point out that the scenario I've outlined is based on the assumption that dark energy will continue behaving in the future as it is now. If dark energy is somehow dynamic and behaves differently in the future, perhaps something else can happen. Whatever this thing we call dark energy is, there seems to be more of it than anything else in the universe, around 68%. The rest of it is matter, but most of that is dark matter. Ordinary matter, which consists of protons, neutrons, and electrons, makes up just 5%. If you thought astrophysics was done and there are no great discoveries left to be made, oh boy, were you wrong. What we know is just 5%. 95% is still waiting to be discovered. And most of the ordinary matter is just hydrogen and helium. All of the heavier elements we find on the Earth make up way less than 1%. This means the materials that make up the Earth are extremely rare in the universe. Life is even harder to find. This is the only planet with clear evidence for it. And it took a series of extremely low probability events to produce life on Earth. Matter had to be created and to outlive the war with antimatter. Hydrogen and helium had to be made. Then galaxies had to form and stars inside them. Then stars had to make heavy elements, and when they died, they had to scatter these heavy elements. And then those elements had to make their way into the star-forming region where the solar system was born 4.5 billion years ago. And then the conditions had to be right for life to arise on this planet, and then to survive and continue evolving for over 4 billion years. It took these and many other nearly improbable events to make you. Early on in this course, the central message seemed to be that we're not at the center of the universe, despite what people used to believe. Our place in the universe has seemed less and less significant over time as we realized that our star is just one of hundreds of billions in the galaxy, and that our galaxy is just one of hundreds of billions in the universe. However, we're now also learning that the universe isn't made mostly of the stuff we find here on Earth. It's made almost entirely of these mysterious things called dark energy and dark matter. What we have on Earth is rare and special. It's also fragile. And that makes it incredibly precious. We need to cherish and protect our planet.